Okay, hello everyone. I wanted to wait for just a second to get a feedback on the chat to make sure that it's coming through. My preview looks wrong, but everything else seems fine. So if someone could just type something into chat there once you can hear me and see the start of the lecture slides. Okay, great. Thanks for the update. So one thing on the Project 4, I'm going to be getting that ready and putting it out tomorrow. I've got the project spec is just about ready to go. The autograder's almost ready. I'm just going through and double checking everything before I post it. The first part of Project 4 is going to be minimum spanning trees, which we covered last time. And the other two parts that are going to be working with TSP, which we're going to talk about on Thursday. So you've got enough to start on part A of the project already, and the project comes out tomorrow, and then we'll have a video. I'll make a video at some point, probably Wednesday or Thursday. I'll get a video tutorial out, and then we'll talk about branch and bound and TSP and traveling salesperson on Thursday. So today we're going to talk about algorithm families. And we're going to look at a couple of different families which are ways to categorize algorithms. Not all algorithms must fit one of these categories, but many do. So we're going to look at different families like brute force. What does it mean to have a brute force solution? Greedy, which we already mentioned when we talked about prims and Kruskal's. Divide and conquer, which we've already talked about a bit in previous lectures when we talked about quicksort, for example. We're going to look at an introduction to dynamic programming, which we'll have a whole lecture on next week, and then backtracking and branch and bound, which we're going to be talking about on Thursday. So when we're talking about a brute force algorithm, a brute force algorithm is something that solves a problem in a simple, direct, or obvious way. And it's not always obvious how to write the code to do this, but the solution is straightforward. The brute force solutions, there's nothing that looking at it you would say, oh, because the code has X, it must be brute force. That's not always true, that it's easy to distinguish it by looking at the code. The upside to brute force is that it is sometimes very simple to implement. The downside is that brute force may be doing more work than is necessary to solve the problem. There may be better ways to do it. Brute force is usually not very efficient, and it's also sometimes not that obvious. So we're going to look at some examples of these different algorithm families as we go through. So one example would be counting change. So if, before you became a computer science major, you might have had a job as a cashier and had to make change when people gave you cash, you always have to give people the right amount of change. That's sort of assumed here, that we have to give them the right amount of change. People get upset if you owe them 70 cents and give them a dime and tell them you're done. But another goal in making change is people kind of expect you to give them the minimum number of coins. If you owe them 70 cents in change and start counting out pennies one at a time, yes, you will reach 70 eventually, but they're going to become unhappy long before you reach the 70th penny. So we usually want to make the correct change using the smallest number of coins. So that's our problem. We've got a definition here, a mathematical definition of it, which is not critical to understanding the problem, but we're going to refer back to it in a little bit. So we've got in our drawer, we've got some set P. P is our set of coins, and each coin has a denomination associated with it, and we can have repetitions. So I could say, like in P, I've got dime, 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 and over in the denominations, I would have 10, 10, 10. What we want to do is we want to make a subset of the coins that we select, S, such that if the S sub j is equal to 1, or is it S sub, yeah. If the S sub I is equal to 1, that means that P sub I is in the set. And if S sub I is 0, it means that coin P sub I is not in the set. A is our amount that we want to return. We've got to have the sum of the denominations equal to A. So the amounts have to total to A, and we want the smallest number of coins marked as 1, 1 meaning true. So we want to minimize the number of coins that are marked as true that gives us the correct amount. So the brute force approach would be, okay, I've got n coins in my drawer. For every coin, every dime, every penny, every nickel, every copy of every coin, I can decide to take that particular dime or not take it. And because I can take or not take every one of those coins, there are 2 to the n possible ways to make a set of change. So we could start out, the brute force would say, ooh, let's just enumerate all of those up front. So there's 70 coins in my drawer. Let's enumerate all 2 to the 70th ways to make coins. And then for every one of those sets, we'll check, does it give the right amount? That means it's a feasible solution. It's not feasible if it doesn't give the right amount. And then we want to, for all the feasible ones, we want to minimize the number of coins that we take. So for example here, if this is what's in our drawer, then I could either, and this is only enumerating the ways to do it without worrying about that there might be more than 1 quarter or more than 1 dime. So there's like 20 rows in this table of, I could take 30 pennies, I could take 25 pennies and a nickel, and this is a lot of work, and this ignores the fact that there might be 50 pennies in my drawer, of which I could pick 30 out of the 50. So there's still a lot of work here, but we can see that after we do all of this enumeration, we could make change with 2 coins. Now there would be, if there was, like I said, if there was 70 coins in the drawer, there would be 2 to the 70th ways to make those coins. And for each of those, I have to do O of n work, because I have to say, okay, for all n coins that exist in the drawer, if I did or did not take it, I have to add the value to my current running total of how much value, and for each one that I take or don't take, I have to count, did I take it or not take it? So we get basically a big theta of n times 2 to the nth is our time to do the brute force solution. And with like 70 coins in our drawer, we would be dead long before we enumerate all the possibilities. I don't know if we'd necessarily be at the sun going dark stage after 2 to the 70th, but that's a possibility too. We'd certainly have an upset customer long before we got it done enumerating all 2 to the 70th combinations. So let's look now at greedy algorithms and how we could apply greedy to this particular problem. So a greedy algorithm is going to make a sequence of decisions. It's always going to make a valid decision. And at any given point, it's going to make the best valid decision that it can. Like, for instance, what would be valid or invalid? Remember when we did prims and Kruskalls? Kruskal will never take an edge just because it's short. It'll take the shortest edge that doesn't produce a cycle. So we're going to make the best decision we can make right now. We're never going to go back and reconsider a previous decision and say, oh, now that I've learned more, let's go change an earlier decision. We're not allowed to do that. What we'd like to see is that if I keep making these locally optimal decisions, does it lead to a globally optimal solution? Does making the best decision I can right now cause me to get the best solution there can possibly be, or not? So the advantage to greedy algorithms is that they may run significantly faster than brute force. The downside is we might not always get an optimal solution. generally we're going to get a correct solution. If we always make correct choices, we will have a correct solution. We will not violate constraints. We might not be optimal. We also might not be able to finish our solution. And we'll look at how that could happen later on when we look at a different problem. Okay, 37 billion years, thank you. So, yeah, upset customers. Okay, so the greedy approach here to making change, we've got to figure out how we're going to be greedy. So the greedy approach is going to be, let's go through our coin drawer from largest denomination to smallest. And if you've ever been a cashier or even watched when they take coins, you'll see their coin drawer starts with things like maybe odd coins like dollar coins or 50-cent coins. And then there's a drawer section for quarters, a section for dimes, a section for nickels, and a section for pennies. So what we can do is I'm going to take the largest coin such that it doesn't give them too much money. So if I currently owe them 20 cents, I won't take any dollars or 50-cent coins. I won't take a quarter. I'll take the biggest coin that doesn't overpay them. And then after I've selected this coin that is not too big, then I adjust the amount. I say, okay, I owed you 70 cents. I have given you a quarter. Therefore, I owe you now 45 cents remaining. I've updated the amount that I still owe you. And then we keep doing that for the next biggest coin that doesn't overpay them. So I'd say, okay, I owe you 45 cents. If I give you a quarter, I now owe you 20 cents. I can't give you a quarter anymore. That would be too big. I give you a dime. I now owe you 10 cents. I give you another dime. I owe you 0. And we stop when we reach an amount of 0 owed. Okay, so Rajiv, what the difference here is that, for one, it may be hard to show that the locally optimal decisions do lead to an optimal. If we can prove that, then it will give an optimal solution. If we just consider a greedy algorithm, it may be hard to do that proof. So we might not be able to prove easily whether or not this one will be optimal. It also may depend on the data. We're going to look at that with coin making. So if we need to, we'll come back to that question a little bit later. All right, so we've got our greedy approach to making change. We always give them the largest coin that wouldn't overpay them. So now if we apply this same strategy to making 30 cents, we can give them a quarter. Now we've got 5 cents remaining. We can't give them a quarter. We can't give them the dime. We can give them a nickel. Now we're down to 0 cents. And we stop. And we've given them the right amount of change. And it equals the same number of coins that we got when we used the brute force approach. So that's good. In this case, at least we've given the right number of coins. Now here's a question which is related to yours. Does greedy always work? So it just so happens that whether by design or luck, the U.S. coin system, although the U.S. coinage system predates the term greedy algorithm, it does give an optimal solution if we apply a greedy algorithm to the U.S. coin denominations. What I'd like you to do is take a few minutes and see if you can devise your own set of coins and an amount such that it does not give the smallest possible number of coins. Given your denominations and your amount, find a counterexample. So take a few minutes and see if you can devise that, and we'll come back and talk about it. Well, we tend to assume here, Samuel, that we've got enough coins to give the right amount in the minimal number. So to make things easier, let's just assume we do have enough coins in our drawer to give the optimal solution. Even if we were missing some coins, we could still give the best possible for right now. So if I was trying to make change for 30 cents and I had no nickels at all, well, I could give them a quarter, and then 5 pennies would be 6 coins. And yes, we would have been better off if we had given them 3 dimes. So it only works if we do actually have the coins to make it happen. So in fact, the question that Samuel just had gives us an example of a set of coins and an answer that doesn't work. If we just take the US system and delete the nickels and say nickels don't exist anymore, if my denominations, so if my amount is 30 and my denominations are 25, 10, and 1, well, then this greedy algorithm no longer works. Another possible example would be, say that my amount that I want to give is 14 cents, and my denominations are 10, 7, and 1. Well, now the greedy strategy would say give them a dime followed by give them 4 pennies, but we could have instead just given them 2 of the 7-cent pieces, whatever we'll call our 7-cent piece. So there's a couple of counterexamples. So here's a problem that sometimes the denominations allow the greedy algorithm to be optimal, and sometimes the denominations don't. So there's one, like he said, if we were to cross out the nickels. Actually, sorry, before we go on to that one. So we could have lots of different denominations here, and we've got a problem that is sometimes solvable optimally, sometimes not. Even if we had deleted the nickels, sometimes the algorithm will be correct for certain amounts. Like if my amount was 50 cents, even if nickels don't exist, I still give 2 quarters. So depending on the denominations, some amounts might be optimal and others won't. So what about if we wanted to devise a new system of coins that we could see would be guaranteed to be optimal, and why it would be guaranteed to be optimal for any amount? So suppose that we're going to make new denominations. When people come to the University of Michigan, they must spend, or actually, let's call it the Beister denominations, the BBB denominations. So when you want to buy things at Betty, you have to give them in Betty bucks. And Betty bucks come in denominations 1, 2, 4, 8, 16, 32, and 64. Now we can see that for any possible amount that I have to make, if I don't pick the 8, but instead if I were to pick a smaller one, I would have to pick at least 2 of a smaller one to make up for the 8. So now, at least with this set of denominations, assuming I have enough of each coin, my change making will always be optimal. Because if I don't pick the biggest one, I would have to pick at least 2 of a smaller one. Okay, so Pratik, I think I've outlined one that's easy to see why it's always optimal. For other ones, I think what you would have to do is do the same approach and say, okay, if I skip taking the biggest one, does taking 2 smaller ones give me a better solution? Here we can see that for this amount, taking 2 smaller ones is never better. Whereas if we go back to the US system without a nickel, we could see that sometimes taking the not largest one is a better choice, like with 30 cents. So it really comes down to, can you provide a counterexample would show that definitely it doesn't work. proving that it is optimal for a certain set of denominations, you'd have to basically do a proof by contradiction and say, well, what if I don't take this one, and instead I have to take a smaller one? If I can prove that taking the smaller one leads to more coins, then I've proved that this set of coins is not optimal. Okay, here's another example we'll use for being greedy. So we're going to talk about sorting in general. So if we look at sorting, before I sort, you gave me a random collection of integers, my array. When I'm done for all I comma j such that I is less than j, that implies that my array sub I is less than or equal to my array sub j. So I've got the precondition and I've got the postcondition that must be true after I'm done sorting. So that's what we want to have happen. In the brute force approach, we could try all permutations. And if we have n distinct values, if we have no repeats, then there are n factorial permutations of the array. So we produce all n factorial permutations. For every permutation, we do the check. Well, the time to run the check takes O of n squared time just to do this verification that for all I less than j, my array sub I is less than or equal to my array sub j would be O of n squared, which then gives us, our total complexity would be O of n factorial times n squared, would be the time to run this through. And we know we can do better than that on sorting. So brute force is terrible, terrible approach. Now we could speed this up properly. We could speed up the verification step. What if I said something like, for all I less than n, my array sub I is less than or equal to my array sub I plus 1. Well, now I've reduced the verification step to O of n, which means that our total now is down to O of n times n factorial instead of n squared n factorial, which is still not quite a win. We're still at the n factorial range. We've got to get rid of all those permutations, but we have found a faster way to verify. Okay, so here's one approach to solving the sorting problem. I could say, hey, let's find the smallest value in the array and let's swap it with the first location. Then, for the other n minus 1, I find the smallest of those n minus 1 and I move it to the second location. I find the smallest of the remaining n minus 3, I move that to the third location, or swap it with the third location. And if we keep on doing that, if we do that n minus 1 times, where we find the smallest one and swap it to where it should be, then after n minus 1 times doing that, the biggest value is left where it must be, and this should look familiar to us. This is one of the elementary sorts that we looked at. This is selection sort. So selection sort can be thought of as being a greedy sorting algorithm in that it does the best thing it can do right now. It finds the smallest unsorted one, swaps it with where it should be. Of the unsorted region, find the smallest of those, swap it with where it should be. What about our other algorithms for sorting? For example, bubble sort. Bubble sort actually is really similar to our verification step. Bubble sorting says, hey, let's compare index I to index I plus 1. If I don't like their order, let's swap them. And we know that that approach does give us an array that's sorted. There's no idea of optimal here. It's either sorted or it's not sorted. But we've done it in less time than brute force. We've done it in n squared time at worst. So we could think of selection sort as being a greedy approach to sorting. We could think of bubble sort as being a greedy solution to sorting. Another example here is a mountain climbing example. So the brute force approach would be, okay, I've got a mountain. I can say, let's say the mountain is no bigger than 1 square kilometer. So I'm going to get out my map, I'm going to lay out a 1 meter grid, and I'm going to go stand in every one of the 1 million 1 meter square areas. And if I visit all 1 million 1 meter square areas, one of those has to be the highest point, or at least it has to contain the highest point. So if I do that for all 1 million of those 1 meter squares, I will have visited the highest 1 meter square on that mountain. So that's the brute force approach. Very time consuming. The greedy approach would say, hey, let's make a decision that increases my altitude. So from where I am now, let's go upward. And I'm never ever going to go downward. Well, if I never go downward, I might reach a point where there's nowhere that I can go up from here. I can only go downward from here, and I've never reached the top without going down. So that would be a place where maybe a greedy approach might not work. See, if we have a mountain that you would draw when you were 3 years old, the greedy algorithm works. But if we look at a more realistic view of a mountain, there's little depressions. As we work our way to the top, we would get to there and say, oh, I can't go downward because I'm being greedy. I only go up. And I found the best point I can from where I started, but I never reached the top. So maybe greedy approach isn't the best way to climb mountains, at least not with a strict greedy rule of never going downward. So actually that slide, there's really, we've looked at a couple of these. Like we looked at selection sort, how is selection sort greedy, how is bubble sort greedy. One of the things I asked you to do at the end of the MST lecture was to prove to yourself that that the greedy approaches, prims and Kruskal's, that they do work. So do they give an optimal solution? Do they always give something that has the lowest total cost? And how do they prevent you from having cycles? So if we want to say, for example, Kruskal is very easy to prove why it is going to be optimal. Because at any point, I will take the shortest length edge that will not produce a cycle, and then thus I have selected all the shortest edges that don't produce cycles. I must have an MST when I'm done. If we look at prims, how does prims prevent a cycle is one of the questions. So because in prims, we only connect something from the inset to something in the outset, we can't possibly produce a cycle. Because the outset has no edges, there are no edges right now between the inset and the outset. So the only way to produce a cycle would be to connect inset to inset. Since we don't do that, prims cannot produce a cycle. And since we take the lowest cost edge that doesn't produce a cycle, we must be producing an MST. Okay, so our next algorithm family is divide and conquer. So the idea of divide and conquer is, let's divide a problem into 2 or possibly more smaller subproblems, and then we solve the subproblems. It's often recursive because we don't know how many times we're going to have to do this. So every time we divide it, we make a recursive call to each region or each section. And our hope, preferably, we're going to get equal sizes. So it says here these often involve log n. Well, often involve log n, it's fairly easy to see why, is that we're dividing by 2. A better question would be, why isn't the complexity always involve log of n? Let's do a counterexample, which is something like in-order traversal. Let's suppose I have an AVL tree. So we know it's balanced. We know we don't have a stick. And so I'm going to make a recursive call to the left half. So my, T of n. my T of n is equal to T of n over 2 for the left half, plus some constant amount C0 for the visiting the current node, like printing it out, plus T of n over 2 for the right half. So that's equal to 2T of n over 2 plus C0. We plug this into the master theorem. We've got A is equal to 2, B is equal to 2, C is equal to 0 because this is a polynomial of degree 0. Plug that into the master theorem and we get big theta of n. Well, that matches our intuition that if I want to print out everything in an AVL tree, I'm going to print out all n nodes. It should take me O of n time. Even though I divided it into 2 halves, I still came up with a complexity that didn't involve log n. So it really depends on the form of our recurrence relationship. Often it will involve log n, like if we do binary search, will be log n, but in order traversal, even though there's a division by 2, we come out O of n. So that's a couple of examples of divide and conquer algorithms. So the nice thing about divide and conquer is we can get a good efficiency out of it. And we get, I put it in quote marks there, the elegance of recursion. The more recursion you do, the more you become comfortable with it. So like we've seen recently, in-order, pre-order, post-order traversals all involved recursion. The downside is that when we do this, if we start out with a big problem, we're going to have lots of base cases. And although the theoretical complexity doesn't change, the lots of small recursive calls do have a non-zero cost. And yes, the theoretical complexity holds, but like we saw with intro sort says, hey, when you get down to those small regions, just do the insertion sort because nobody beats it. The other downside to the divide and conquer approach is that sometimes it's dependent on the initial state. So one example is that binary search. We cannot do the binary search if we don't have a sorted array. Another example would be going back to quicksort. The initial ordering might determine whether I produce a good partition or a bad partition. So I may not get my best efficiency in certain cases of certain permutations of the values. I will still divide it into 2 regions, but they might not be of equal sizes. They might be n minus 1 and on one side, the pivot element, and then 0 on the other side. Now, combine and conquer is a subset of divide and conquer. So combine and conquer is just a slightly different approach would be like merge sort. Merge sort, really a better name for this would be conquer and combine. But combine and conquer just sounds better in English, so we're kind of stuck with that name. But if we think about merge sort, we really conquer each half. We say, okay, if I sort the first half and then I sort the second half, it would be easy to combine those 2 sorted regions into 1 sorted region. So this is the split down here at the bottom, that divide and conquer is top down and combine and conquer is bottom up, isn't always true. Divide and conquer, because it involves recursion, is often top down. Very, very common to see divide and conquer be top down. Combine and conquer, merge sort, we looked at a top down solution and we looked at a bottom up solution. But we can, for a combine and conquer, we often can do a bottom up, but it's not the only way to do it. Whereas with divide and conquer, it'll almost always be a top down approach is the easiest way to implement it. So combine and conquer is really just a subset of divide and conquer. So like I said here, algorithms we already know, binary searching of a sorted list, quicksort, merge sort are ones that fit into those categories. And in-order, pre-order, post-order traversal are all divide and conquers. Okay, so for dynamic programming, the idea of dynamic programming is that we're going to remember partial solutions to smaller subproblems when those smaller subproblems are related or, better yet, repeating. So if I've already solved this subproblem and I saved the result when I calculated it the first time, the next time that you need to solve that same smaller subproblem, we say, hey, do I have it saved? If so, let's look it up instead of recalculating it. And the upside to dynamic programming is that it can turn things that are exponential into It can turn something that's exponential into polynomial complexity. And the downside to dynamic programming is it's a bit of a difficult thing to grasp. We're going to have a whole separate lecture on dynamic programming coming up next week at some point. Yeah, next week. So we're going to have a whole lecture on this topic. And it's also something where every dynamic programming problem, you have to look at it and see what is the subproblem. How do I organize my saving of those subproblem values so that I can look them up? Now, one example we're going to do today is Fibonacci numbers. So if we do a simple Fibonacci definition, f of n is equal to f of n minus 1 plus f of n minus 2. And we've got a base case where f of 1 is equal to 1 and f of 0 is equal to 0. So there's our recursive definition with our base case. If we look at even not too horrible a Fibonacci number, let's say I want to calculate f of 6. Well, to calculate f of 6, I need f of 5 and I need f of 4. But think about a recursive solution to this. A recursive solution would start trying to solve f of 5. F of 5 then needs f of 4. Wait, to get f of 4, I need f of 3. To get f of 3, I need f of 2. To get f of 2, I need f of 1, which is a base case. I need f of 0, which is also a base case. Now, without dynamic programming, we would then go back to f of 3 and say, now I need, for f of 3, I now need f of 1, which is a base case. That's not bad. Go back to, now that we've got f of 3, I need to finish f of 4. So to finish f of 4, I'm going to change colors here. To finish f of 4, I need f of 2. So I have to recalculate f of 2 by calling f of 1 the base case and f of 0 the base case. Well, now that f of 4 is done, we can do f of 5. To do f of 5, I need f of 3. F of 3 needs f of 2, which needs f of 1 and fib of 0. And it needs, so now we've got f of 2. We can calculate fib of 3. We can finish fib of 3, needs fib of 1, which is a base case. Now we've finished fib of 3, so we've can finish fib of 5. So now I'm back to, hey, I want to finish fib of 6. I need fib of 4 all over again. So I need, basically, this whole subtree goes under fib of 4. So you can see how we start repeating a lot of work. What would be better is, hey, the first time I calculate fib of 2, let's save the result. So then if we save the result for fib of 2, then I can eliminate that recalculation. And then if I save the result of fib of 3, I can eliminate that recalculation. And if I save the result of fib of 4, I can eliminate that recalculation. And it just basically becomes a new base case almost. I look it up, I say, do I already know this one? Yes, I do. Okay, here it is. So we're going to look at, like I said, we'll look at how to do this. And really what we're going to do in dynamic programming is we're going to trade memory to get more speed. We're going to, if the amount of memory is reasonable, I'm going to sacrifice my memory constraints and make my memory constraints a little bigger in order to make my time constraints much smaller. And like I said, we're going to do a whole lecture on this coming up next week. And also, sometime soon, I'm trying to get the Project 1 spec done. I'll get the next couple slides uploaded to Canvas in the next couple days. After I get the project done and I get the AutoGrader up, then I'll get the next couple slides uploaded so you can take a look at this in more detail. Okay, so up until now, we've actually talked about two different types of problems that were solved by different algorithm families. And we didn't mention their types, actually, but now we need to before we talk about the next few algorithm families. So some of the problems that we want to solve are what are called constraint satisfaction problems. We want to satisfy a given set of constraints, and if we can, how do we do it? So, for example, sorting is an example of a constraint satisfaction problem. You gave me an unsorted collection of data. I gave it back to you so that it met the constraint of array sub I is less than array sub I plus 1 for all valid i's. Another one would be Project 1. Is there a way to get through this maze? Can you find me a set of directions that solves it? Another one would be spanning trees, not a minimum spanning tree, but just here, given this graph, can you give me a set of edges that produces a tree that connects everything? So another type of problem we might want to solve is an optimization problem. Optimization problems generally have constraints that we have to meet, and beyond that, there's some sort of objective function that we want to minimize or possibly maximize. Minimizing tends to be more common. People don't say, find me a way to fly home and I want to spend the most money on tickets that I possibly can. So optimization tends to be more common to be minimization, but there are places where we do want to maximize things. And we'll look at an example some point in a future lecture. We'll look at an example when we talk about this in more detail and go through there's a whole nother lecture on these two topics. So for example, here are our optimization problems. Making change, we have to meet the constraint of giving the right amount. We also then want to minimize the number of coins that give the right amount. Or for the minimal spanning tree, we do want to produce a spanning tree. We want everything to be connected either directly or indirectly, and we want to have the minimum total cost of the edges is what we want to minimize. So when we do a constraint satisfaction problem, we can, let's add that word out front, we can stop when a satisfying solution is found if one solution is sufficient. If the person says, find me every way to sort this array so that it's sorted, so we have to say, okay, well, I put, Charlie Sheen before Martin Sheen, okay, but I put Martin Sheen before Charlie Sheen. They're still sorted by last name. So usually when someone wants a constraint satisfaction, usually they might be satisfied with one, or we might give them all. It's usually one or the other. Either we're going to give them the first one and we'll stop, or we'll enumerate every possible solution to their problem. In an optimization problems, we usually cannot stop early because most of the time it's hard to know that our current solution is the best. What we usually have to do is find and go through every possible solution, and we're going to pick the best one of the ones that are feasible. Feasible meaning it hasn't violated any constraints. So really, we don't actually generally maintain an entire feasibility set. What we're usually going to have is the best so far, and that's a complete solution. So I'm going to keep track of my best complete solution so far and my current partial solution. So I'm going to build up my solution a piece at a time. When it becomes complete, when it is at the level of, hey, I've picked everything, I have a complete solution now, then I would say, hey, is my current solution that's now complete, is it better than the best so far? If it is, let's change the best so far to be equal to the current one, and then we keep searching. And again, it's hard to tell when I have a current solution that's better than the best so far. It's usually very hard to tell, oh, it'll never ever get better than this. Usually that's hard to answer. So we generally have to go through every possible way to solve the problem. Every time we find a complete solution, if it's better than the best so far, we update the best so far. Now, when we want to do these types of problems, either constraint satisfaction or optimization, we can rely on backtracking to solve a constraint satisfaction. We can rely on branch and bound to do optimization. It doesn't mean we have to go that way. If we don't find something better, this way will always work. So for example, with sorting, we don't need backtracking to do sorting. There are other ways to do sorting that work and are faster than backtracking. Because backtracking could take that exponential or factorial time. Whereas if we've got a better solution that runs faster and it does give us a valid solution, we should go with that. But if we can't find anything better, then backtracking will always work. We can always go to backtracking if we never find a better way to do it. For an optimization problem, if we can't find a greedy way, if we can't find a dynamic programming way, if we can't find a better way to do it, we can always solve it with branch and bound. Now, backtracking algorithms, the way they proceed is that we're going to systematically consider all possible outcomes of every decision, but if we don't satisfy constraints, we're not going to keep making more bad choices. So this is like our depth first search with pruning. For example, when we did graph coloring. If I say, okay, I colored the first state red, and since it was the first state, it didn't violate any constraints. Let's color the second state. Let's try coloring the second state red. Oh, look, I violated a constraint. The red one's next to one that's already red. I would backtrack and redo a decision. I wouldn't say, let's color a third state red and a fourth state red and a fifth state red. I would prune this choice. I would say, okay, red for state 1 followed by red for state 2 does not work because they are adjacent. Let's change our mind about state 2. Let's color it blue. Oh, that didn't violate a constraint. Okay, if it didn't violate a constraint, then I can go and color state 3. State 3, let's start back at the beginning. Color state 3 red. If that touches state 1, we say, nope, that violated constraints. So let's draw it out. So I've got a state A, B, and C. And let's just assume we've got a completely connected graph here. So I tried red for this one, no constraint violations. I tried red for this one, constraint violation, change it to blue, no constraints violated. So let's go to state 3. I start out at the beginning of my colors. I say red. Oh, red doesn't work. Let's backtrack and try blue. Oh, wait, blue doesn't work. Let's backtrack and try green. Green doesn't violate any constraints. We can go in now and we can go color state 4, state 5, state 6, etc. So that's what we mean by pruning, is we don't consider more bad choices after we find a constraint violation. The nice thing about this is it does eliminate our exhaustive search. And we saw when we did the graph coloring how we could prune away big sections of the tree. Or wait a minute. Graph coloring is still upcoming, I think. I gotta look at my slides. Okay, yep, sorry to do that. I sometimes get out of order because I'm so used to the slides, sometimes I forget what order they're going in. So we're gonna come back to this one next time, and we're gonna see how we eliminate the exhaustive search, and we're gonna look at one that I actually got a program that tells you how much of the search you eliminated after you run it. Now, the downside is that even though we prune out sections of our search space, the search space could still be pretty large. So we're going to run faster. We may not run fast, but we will run faster than if we did every possible combination, even considering red, 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 red. Let's just keep going red, even though we know the first two were invalid. Okay, oh gosh, it's right here. Sorry, I should have looked at these beforehand. So here's what we're talking about is the graph coloring. So the question is, if I gave you a graph, could you color it with 4 colors so that no 2 vertices are connected by an edge that has the same color? Depth first search. Depth first search was, remember, like if we do either recursion or we use a stack, we tend to go downward before we go sideways. So that would be like project 1 with a stack would be an example of depth first search. Okay, so sorry for my confusion. I should have been a little bit more ready than I am. I know, like every single slide, I just don't always remember which slide comes next. So we've got a problem here. We want to know, can I color a graph with 4 colors? What I want you to do is take a minute, come up with an example of a graph that you can color with 4 colors, or less would be valid too. If you don't use all the colors, it's still 4 colorable, as long as no 2 adjacent ones have the same color. Oh, well, look, in the previous slide, I made one that does. What about a graph that cannot be 4 colored? So take a few minutes and draw a few graphs out. I'm going to add a blank slide in here. Oh, and now you're getting my view, which is painful. We've dealt with this in person. We can deal with it on recordings. Okay, so we already gave one example on a previous slide. So if I've got, say, even just 3 vertices, it's 4 colorable. If I've got 4 vertices, it's 4 colorable. Wait, is 4 vertices always 4 colorable? What if I had something like just 2 vertices? I've got vertex A, vertex B. They're connected to each other, and A is connected to itself. Aha! That's one of the reasons why we said we were going to stick to simple graphs. If we don't have a simple graph, there's no coloring that works for this graph, no matter how many colors we have. So unless we say otherwise, we're going to assume we don't have those self edges. We have a simple graph. So if we have 2 vertices, it can be colored with 2 colors. If I had 4 vertices, A, B, C, D, I can color them even if they're completely connected. There's 4 of the edges, here's a 5th edge, and so I don't get ambiguous with it crossing, there's another edge. So if I pick like red, green, blue, and orange, I can color that. What if I had more vertices though? What if I had like 5 vertices and I've got A, B, C, D, and E? Now, if those are the only edges that exist, then this graph is colorable with 4 colors. In fact, this graph is colorable with 2 colors. I could go red, blue, red, blue, red. Oh, wait. Oh, I guess I can't do it with 2 colors. So if I go red, blue, then I would need a 3rd color for the last one. So this one's colorable with even just 3 colors. But what if I add more edges? What if I make a completely connected graph If I make a completely connected graph with 5 vertices, it can't possibly be colored with 4 colors because I pick red, green, blue, orange. I'm fine up until now, but then there's no color that works for vertex E. It'll be adjacent to one of the others. So a completely connected graph with 5 vertices can't be colored with 4 colors. In fact, a larger graph that has a region in it like this, where 5 vertices are completely connected, doesn't work with 4 colors. Now, when we're talking about a map, if we're talking about a map, maps of countries or states in the US can always be colored with 4 colors. And there's a reason for that. And there's a slide here, let's color this graph. We'll come back. We're going to do lots of coloring this graph in just a minute. So one thing is that if we have a map can be turned into a planar graph. So a planar graph has a definition. A planar graph is a graph that can be drawn with no crossing edges. So when I want to convert a map to a graph, what I do is I make the states or the countries or whatever I'm doing, I make the states become the nodes, and I make shared borders become edges that connect those 2 nodes. So for example, on the next slide here, we've got our graph of states, and I didn't fit the names into the states on the graph, but the on the map, but in the graph I added the state names in each circle. So we've got the map over on the left, we've converted it to a graph, and it turns out that maps can turn into planar graphs. Planar graphs are always 4 colorable. Sometimes it can be done with less, but a planar graph never needs more than 4 colors. And if we go back a few slides, let me find the ones that I drew on. This one, notice this graph, this on the right, cannot be drawn without crossing lines. Whereas the one on the bottom left here, this one, I was able to, instead of crossing AD across the center, I moved that edge across the outside. And even in the right-hand graph, even if I were to erase some of those edges and move them outside, I'd eventually run into a place where there's at least one edge that I can't draw without crossing. And if I cannot draw it without crossing an edge, it's not a planar graph. And therefore, it's not guaranteed to be 4 colorable, and probably is not. Okay, so where were we? Right here. Okay, so we've got our map of the states, and we've got our 4 colors, and we could start running through colors on this. Now let's look at a couple. There's a solution here. So there's a solution here that works with 4 colors. There's a solution given, there's trying to work out a solution with 3 colors. So if I were trying to work out a solution with 3 colors, I could start going through it. So I could, let's say I colored Mississippi red, Tennessee blue, North Carolina green, South Carolina red, and then I say, well, South Carolina red here, well then what happens? What do I do with Georgia? Georgia can't be anything. It can't be blue because it's next to Tennessee. It can't be green, it's next to Carolina. It can't be red because it's next to South Carolina. Georgia has no possible color, therefore South Carolina can't be red. I've got to backtrack and try no color worked for Georgia, so I've got to try another color for South Carolina. And so there is a 3 coloring that does work for this. Now let's look through how we could do this approach. So what I'm going to do is I'm going to start drawing out, start enumerating my choices. So for every vertex, I'm going to consider all 4 possible branches. Then for vertex 2, vertex meaning what color did I color this vertex? So I'm going to say, hey, vertex 1, let's color it all 4 colors. Let's consider those branches. Then let's look at vertex 2, we consider its branches, vertex 3, etc. So let's draw this out. I'm going to make a new slide here. And yeah, I forgot about this stupid problem on the PowerPoint. Eventually, I'm going to upgrade to the new PowerPoint, which they said they completely redesigned the user interface, which makes me a little bit afraid. I have not been upgrading to hopefully get rid of this bug. Anyway, let's look at how we would enumerate this. And it's what's called a decision tree. So what we're going to do is we're going to say, hey, let's look at the possible ways to color vertex 1. So vertex 1 here, let's try coloring vertex 1 red. Now let's try coloring vertex 2. If vertex 1 is red, let's try coloring vertex 2 as red also. Now, if vertex 1 and vertex 2 are adjacent to each other, we would say, hey, this is a constraint violation. Let's not try coloring anything else red. That's not going to work. Let's make a different decision for vertex 2. Let's try coloring it blue. Okay, since we've only got 2 vertices, we know there can't be a constraint violation. So now, let's try coloring vertex 3. Let's try coloring vertex 3 red. Oh, well, if vertex 3 was adjacent to vertex 2, or to vertex 1, that would be a constraint violation. Let's try coloring it blue. If the vertex 3 now is adjacent to vertex 2, that would be a constraint violation. Okay, let's try coloring vertex 3 green. Well, we know there can't be a constraint violation. We compare vertex 1, we compare it to vertex 2. It doesn't violate any constraints, so now we can start coloring vertex 4. And vertex 4, let's say vertex 4, we try red, etc. So that's our decision tree that we're going to make. And then let's say we either did or did not find a solution. Eventually, we're going to have to go back and make a different choice. Let's say we're enumerating all possibilities. We would eventually have to go back and undo all of our choices and make a new choice for vertex 1. So if we're enumerating every possible way to color this graph that is a valid coloring, we would eventually, whether we find a solution or not, we would go back and pick a different color for vertex 1. Okay, so if we suppose that there is an edge V1, V2, among those 16 branches, remember? So I'd have V1 would be colored blue, red, blue, green, or orange. Then for each of those, I would color vertex 2, red, blue, green, or orange. And some of those are going to be dead ends, like our red followed by red was a dead end. Blue followed by red is okay, but blue followed by blue is a dead end. And since V1 and V2 are adjacent, red is a dead end, blue, green, orange. That's 1/4 of the tree that we've eliminated. Since when I get red as a constraint violation, I never color vertex 3. If vertex 1 and vertex 2 are adjacent to each other, by pruning invalid choices, I've eliminated 1/4 of the search space at the highest level. And then lower down, I might eliminate other portions also. So we're going to branch on every possibility. We're going to maintain one or more partial solutions. Really, this goes back to what I said earlier. Really what I need is, if we're optimizing, I would need a best solution so far and a current solution. If all we're doing is trying to enumerate them, we really could just print them out. So as we get to a solution, let's just print it out and let the person see the solution. And then we'll go through and make other choices. So every time we have a partial solution, as we're building up this partial solution, I've colored one vertex, I've colored two vertices. We're also going to prune anything that doesn't work. Okay, wait, I got a question there. So, but we also considered red, blue, red. We don't have an easy way to eliminate different colorings that are similar to old colorings. So if I eliminate red, red, I also have to discover that I eliminate blue, blue. I can't just say, oh, blue, blue is like red, red, let's eliminate it. So if so we will have to consider, like if red, blue, red was a dead end, we'll have to consider blue, red, blue later on. So yeah, we'll never go red, red is a violation, let's color more things red. Once we see that red, red is a violation, we won't color a third vertex until we get no violation after two vertices. So hopefully that clears that up. Okay, so we're going to backtrack on every possibility, and we're going to prune things that don't make sense, and that's going to eliminate some of our possibilities. So why is this better than enumeration? Well, we kind of showed that when we did our pruning here. If V1 and V2 are adjacent, we're going to eliminate 1/4 of the search tree at least, and possibly more later on. Now, so here's our what's called the M coloring algorithm. So this is looking at this is looking at how would we do this. It says we've got an input is n, our number of nodes, m is the number of colors we're willing to use, and then we've got this adjacency matrix of what vertices are adjacent to which others. So it'd be filled with true and false. And we're just going to output all these possible colorings. So here's our algorithm graph coloring. Now wait a minute, it says index I is the only parameter. Wait a minute, didn't we just say our inputs were n and m and w of those? Where did I put all of those? Well, I could have made more parameters to this. I mean, granted, it's an algorithm. We don't have to be super careful about everything. But if I was trying to implement this, I would say, well, wait a minute. If I is my only parameter, where did n and m and my whole adjacency matrix go? I could add them as more parameters. But that would be inefficient. I'll show you why. If I add more parameters here, like m and n and my big matrix w, then in my recursive call down here, I would have to add m and n and w to it. Now, if I was implementing this, is this recursive call tail recursive? It's the last line of code, but it's inside of a loop. After the recursive call, there's more left to do. I've got to update the loop variable. I've got to check if I've reached the end of the loop yet. This is not tail recursive. If it's not tail recursive, that means it can't reuse stack frames, which means every recursive call has to push 4 things onto the stack. Well, if I made this a member function of a class, I could make m, n, and w member variables. So I'd make this inside of a class. I make m and n and w and anything else I need. I make them member variables, and I only have one parameter to push onto the stack every time. So, like I said, in an algorithm, we get to hide away details like that. But it's actually, we're showing you a good way, even in the algorithm, is make those other things member variables, make this a member function. So what this says is that if we're trying to color a graph, assuming everything else is member variables, I'm trying to color index I. If I'm trying to color index I, I'm going to check and see if it's promising. And we've sort of got a chicken and egg problem here. What is promising? Promising is basically saying If it's promising, you haven't violated any constraints. So if I have not yet violated any constraints, let's see if I have colored all the vertices. If I haven't violated any constraints and I have colored all of the vertices, let's print this one out. I've got a solution. So I print this one out. Else, if I haven't colored all the vertices, I've got to run through a loop of all possible colors. Let's try to make this vertex a new color. So I would start out, I would say, hey, let's start coloring vertex 0. Is 0 equal to n? No, I haven't colored n vertices yet. So, or also I should have said, is it promising? Well, if I haven't colored any vertices, there can't be any constraints violated. So, is it the level of a solution? No, you haven't colored n vertices yet. You've colored 0. So let's pick a new color for vertex 0. Let's pick a new color for vertex 0, and then let's make a recursive call for vertex 1. Vertex 1, we say, have you violated any constraints yet? No. Have you colored all the vertices? No. Okay, let's run through a loop and pick every possible color for vertex 1, etc. So that's really, when we looked at the decision tree, that's what the decision tree isn't an actual data structure. It's a representation of how the search would be carried out given this algorithm. So we've got promising on the next slide. Promising says, given index I, let's start out at j equals 1, and let's compare vertex j to vertex I. So I'm going to check our vertex A and vertex I and vertex j. Are they adjacent? And do they have the same color? If they do, we violated constraints. If not, we keep on going and we check every other vertex that's already been colored. And really, I goofed because I've been saying 0. 0 makes more sense here. Let's start this out at 0. So it makes it easier to translate, and it makes it easier to see the ending condition, I think, if we start at 0 here. So we start out at 0 and we say, hey, let's compare vertex 0, 1, 2, etc. to vertex I. Well, at the beginning, when I is 0, there can't be any constraints violated. The loop doesn't run, and we say, true, you're good. You're still promising. You haven't violated constraints. Then when we move on to other ones, we compare everybody who's already been colored to vertex I. We never compare vertices to each other. So I never say, hey, you're coloring vertex 4, let's compare vertex 0 to vertex 1. No, when you're coloring vertex 4, let's compare vertex 0 to 4, 1 to 4, 2 to 4, and 3 to 4. I don't consider comparing 0 to 1 because I never would have reached vertex 4 if 0 and 1 were a constraint violation. So to check promising, I only have to check the newest vertex versus all previously chosen colors. And so there's our algorithm over there. Now we've got an algorithm. Let's run through our graph color. Let's say we go through, we call it on vertex 0. Let's say the states are in order by alphabetical order is their number. So when we call this on index 0, really we're talking about Alabama. So we say, okay, Alabama, let's run through all possible colors, and the colors, we'll enumerate them at the bottom, are red, blue, green, and orange. Okay, so we say we're coloring vertex 0. Have we violated any constraints yet? No. Have we reached a solution? No. Let's color this one red because it's the first color. And the people in Alabama are happy because it's red. Anyway, then we make a recursive call. We say, let's color vertex 1. Okay, so alphabetical order, vertex 1 would be Florida. We say, vertex 1, are you still promising? Yes, you're promising because you have not violated constraints. Okay, let's run through all possible colors. Let's color vertex 1 red. Let's make a recursive call to vertex 2. Vertex 2, are you still promising? No. Promising says no because I'd like to color Georgia, but we've violated constraints already. So we go back to here, and we go back through this loop. We say, okay, Florida, you've got to pick a different color for Florida. Let's make it blue. Let's color Georgia. Have we violated constraints so far? No. Have we reached a solution? No. Therefore, we can start picking colors for Georgia. We try R, and we make a recursive call to the next state, which would be, looks like Mississippi is next alphabetically. We make a recursive call to vertex 3, but we say, oh, wait, you're not promising. You've already violated constraints. Recursion unrolls. We go back to Georgia, and we're in the middle of a loop. We pick a different color, blue. Make a recursive call to vertex 3, Mississippi. Are you promising? No, you violated constraints earlier. Okay, unroll the recursion, go back to the for loop, pick a different color for this one. Try, whoops, green. That's terrible G. Okay, so let's try a green here. Okay, let's make a recursive call to Mississippi. Are you still promising? Yes, you're still promising because you haven't violated any constraints. Let's try a new color for Mississippi. All right, so let's try coloring Mississippi red. We make a recursive call, discover we're not promising, try blue, make a recursive call. Recursive call here would be North Carolina. Have we violated any constraints? No. Are we at the level of a solution? No. Let's try red for North Carolina. Let's make a recursive call to South Carolina. Have you violated constraints? No. Let's try a color for South Carolina, red. Let's make a recursive call to Tennessee. Have we violated constraints? Yes. We've got to change this one. Go back, change it to blue. Call Tennessee. Have you violated constraints? No. Okay, let's try coloring Tennessee. Can you color it red? Make a recursive call. We're now making a recursive call on the nth state. There is no nth state. We say, is it promising? No. Okay, go back and color state n-1 blue. Make a recursive call. Is it promising? No. Unroll. Try it with green. Make a recursive call. Is it still promising? No, because it's next to Georgia. Okay. Undo the recursion. Try it with orange. We've found a solution because this is still promising. It doesn't violate any constraints. I is equal to n. We've colored all the vertices. Let's print out this coloring, and then let's backtrack some more and find some different colorings that can work. So that's how the graph coloring works with the states here. So when is backtracking efficient? The nice thing about backtracking is it's going to avoid looking at large sections of the search space by doing this pruning. We saw if the first two vertices are adjacent, we've eliminated 1/4 of the search space. The problem is if we've got O of some constant to the nth power, how bad is this? So how bad is the complexity? I'll get to your question in a second, Rajiv. So how bad is the complexity here? Let's go back to our recursion tree. I had to pick 4 colors here. Then for each of those, I had to pick 4 colors here. Then I had to pick 4 colors here. Then I had to pick 4 colors here. That's 4 to the nth power. So graph coloring, the complexity of this is O of 4 to the nth power. So even if we can eliminate large sections of it, we've still got some small portion of 4 to the nth could still be really bad. Okay, let me look at your question. Because remember, Rajiv, we're only checking vertex I, something that's already colored. We're checking vertex I, which is the most recent one, to V color sub J, and notice the and in here. and we can repeat a color as long as it's not adjacent. So you missed the and part of it. Okay, so there's the when is backtracking efficient. So it is going to reduce our runtime. It might not reduce our complexity class. It's actually a really hard question. Have you pruned enough to change the complexity class, or are you just a bad complexity class with lots of pruning? Is a hard question to answer. And it's going to involve a lot of pruning. Now, some places we can see where it will be enough is if we've got a highly constrained problem, like if there are lots of adjacencies, we will see that we will eliminate colorings quickly because the pruning will occur very often. So if there's a lot of constraints, we'll prune things very quickly. If it's under constrained and we're happy with one solution, so if there's very few things adjacent and we don't do much pruning, if the user is happy with one solution, we should find that one solution quickly and then we can stop if they're okay with that. Now that's another thing that it brings up is back here. If I wanted to be happy with one solution and wanted to stop, how do I stop after this print occurs? Well, I could put an exit 1 after it, and that's a kind of a brute force way to halt. It does halt, but it's ugly to do an exit in the middle of a function. If I can't say break here because I'm not in a loop, I can't say return because I am returning. As soon as this print is done, I'm returning. The easy way to stop this thing after one solution that's not the sort of brute approach of using an exit would be we could throw an exception. I could throw an exception, and at the upper level, we could say, oh, I've caught the printed a solution exception, I can stop now. And that would mean the whole program doesn't have to exit, but we've got a way to stop the recursion, is to throw an exception down in that recursive function. Okay, so that's when backtracking is efficient, is if we get a highly constrained, we'll prune lots and lots and lots. If we're happy with the first solution, we can stop even if it's under constrained, we'll stop quickly. So, summary overall, and we don't leave just yet, we got a few more slides after this. So the summary, we've looked at brute force and greedy. We've talked about divide and conquer and dynamic programming. Divide and conquer, we've actually seen a decent number of those already. Dynamic programming, we're going to have a whole future lecture on that. And we've looked at backtracking so far. We looked at one example of backtracking with the graph coloring. We're going to do another example of it next time. And we're also going to look at branch and bound next time. And we've got a different example for backtracking next time. We're going to do n queens. There's code. If you want to look at the next set of slides and you want to look at more at backtracking, there's in the Canvas files sample code, there's an n queens problem in there. Where we're going to try to put n queens on an n by n chessboard without any queen taking any other. And when we look at that, we're going to do something. I'm going to test it today so you can make sure tell me that it worked. We're going to fire up Visual Studio and we'll actually run the program, and it's going to tell us how much of the search space we pruned. Now, before we leave, I want to give you some tips and tricks for P4, which is coming out tomorrow. So, in P4, one of the nice things is the vertices are numbered in the order that you read them. So when you read an XY coordinate, the very first one you read is vertex 0. The next one is vertex 1. So that makes it really easy to keep things in a vector, and their index is their vertex number. When we look at, there's 3 parts of Project 4. So the 3 parts of Project 4, Part A, is MST, and Part A, MST, you're almost good to go. You've got everything you need to know about MST to start implementing it. There's one tricky thing in the project that you're going to have to work around, which I'll talk about in a second. In Part B, we're doing what's called fast TSP, and in Part C, we're doing what's called optimal TSP. Now, Part C, this is going to be the next lecture, Lecture 22. The branch and bound is all about Part C. Part B is going to involve some Google searching. So next time we're going to talk about what it means, what the TSP is in general. After we talk about TSP and what optimal TSP means, you're going to know a lot about how to do Part C. For Part B, once you learn what TSP is, you're going to do some searching on what's called heuristics. Heuristics for the TSP problem to find something that's O of n squared and gives a pretty good solution. Now, what we're going to be doing is we're going to be setting up a drone delivery system for campuses. So we're going to use U of M as an example, but we really want a generic system that we can then sell to other campuses to deliver like snacks around campus. Now, granted, as a professor, I'd rather not have snacks delivered to the lecture hall, but maybe you could pick it up outside before you come in. So you're going to have a drone fly down, drop off your snacks, and then fly away. So in Part A, we have one restriction. In Part A, we're going to find some really super fast drones. So if we look at campus as a rectangle, because that makes it easier, we're going to pretend that the medical campus down here is a little bit special. Our super fast drones cannot zip in and out of the medical campus directly. The edges are not safe. So what you'll have to do is there's going to be at least one location at the edge. There might be a couple locations over here, and there might be a couple locations on the medical campus. You're not allowed to go directly from one that's non-medical to one that is medical. That would be disallowed. Instead, you would have to go from here to there and from there to there. And if you cut corners there, that's okay. You just can't go from one outside the medical campus to one inside the medical campus. So for the MST, and fast TSP, for parts A and B, you've got possibly 50,000 vertices. You can't afford a distance matrix. You just can't. It would be 50,000 times 50,000 times 8 bytes each would be a 20 gigabyte distance matrix. You're going to have to calculate it. So when you calculate, you'll say, oh, I need the distance between like vertex A up here and vertex B down there. You calculate Euclidean distance. What if I wanted the distance from vertex A on the not medical campus to vertex C on the medical campus? If you are my Euclidean distance function, I'm prim. Well, let's switch roles. You're prim. I'm your Euclidean distance function. You ask me what's the distance between A and B. I say 53.7. You ask me what's the distance between A and C. I'm returning a double. What can I return to you that would make you prim not use that edge? If I give you infinity, you won't use that edge. So prim, when you do part A, don't make prim worry about medical, non-medical, border. Prim doesn't need to know that stuff. Make the distance function, or better yet, functor, say infinity. If the calculation says infinity, prims will look at it and say, well, infinity is not better than what I have. I won't use that. So that's the trick to making prim easy, is don't let prim know about medical versus non-medical. Just let the distance calculation take care of that. So in part A is the only one that has to worry about medical versus non-medical. In parts B and C, you can go anywhere. So in Part C, OptSP won't have more than 40 vertices. Can you afford a distance matrix now? Yeah, that looks more reasonable. So start with MST. You now, after we talked about how to do the distance calculation, you have everything you need to start on Part A when the spec comes out tomorrow. And then Branch and Bound next lecture gives you everything you need for OptSP. TSP slides are going to have gen perms that we're going to use. And also I'm going to put in a text file on Canvas so that you can copy and paste, because copying and pasting from PDFs is dangerous. For the MST, so for Part A, is it dense or is it sparse? Now I sort of gave it away on this one when I said prim. When I said you are prim. Think about, though, is it safe? Oh, I should have updated this. I know I updated the slides. This is supposed to not say land and water and coast. This is supposed to say medical, non-medical, and border. So I updated the slides. I guess I grabbed the wrong version on my tablet. So for fast TSP and OptSP, the graph is completely connected. And which algorithm should you use for MST, and think about that. Now, one thing I want to do before people leave is I'm going to switch screens here. I just set it up so that supposedly when I switch to Visual Studio, it's supposed to switch you over to Visual Studio on the recording. So that's what it looks like. I just want you to let me know if you can see Visual Studio instead of the slides. My broadcast software says it is, and I don't want to open anything up. Oh, let's open up word count demo. So let's open up word count demo, and the next question is, for someone that's not on their phone, if you were actually on like a laptop or a desktop, can you read this code is the next question. So I'm going to switch back to my iPad source, and hopefully you can answer that question. Okay, so yes, you can see it. The next question is, yes, is the code actually visible at that font size? Okay, so now you're seeing slides. Okay, so it's switching back and forth, it sounds like. Okay, I guess I'm going to have to go look at my video later on and I'll answer it for myself. Okay, what I'll do is I'll make a private practice video to try this out and test it a little more. Yep. So I'll play with it more myself, and I'll do it. I shouldn't have made you do my work for me. I'll just make a separate video for that. Okay, I'll stick around in the slides now. If there's any last minute questions, great. And if not, I'll end the stream in another minute or two. So I'll look at the video, what happened there, and see what's going on, and I'll practice a little bit more. Okay, well, I don't see any new questions yet for the actual slides, so I'll close this, and then it'll be in office hours tomorrow, and then tomorrow probably about noon is when the project spec will be out. Take care, everyone.